So yeah, today, third lecture, and the first lecture actually on the mathematics of causality. And after we have seen in the first lecture, obviously we have seen some glimpses of what is to come here today, but it was more on the motivational level. We were not really digging into what it really means. Last week we covered all the basics, right? So probability theory, statistics, independence, graphs, all these things, different representations. And well, today we are going to talk about the causal hierarchy, right? Like about Pearl's hierarchy, about these famous observational, interventional, counterfactual, all these distributions, right? What they mean, how they are defined, and so on and so forth. It's going to be a lot of math, but with a lot of examples as well. I'm trying to guide us through there so that we really develop an understanding of what's going on. So a brief overview. So we have 3 sections, and the first is going to be what we call here a representation of reality. So that's what we really aim to do, or what Pearl did, yeah. And it's going to be, some philosophical justification, and then essentially the solution to it, which will end up being the so-called structural causal model. Then in section 2, we will really look at these models and see them from the perspective that they are data generating processes, right? So they induce these different distributions I just mentioned. And then in section 3, we're actually going to cover the theorem behind all of this, which really shows that there's sharp boundaries between these levels, which essentially just tells you that, causal inference actually makes sense. It's a sensible concept. So let's kick things off with section 1, a representation of reality. So it's going to be about a mathematical object that captures not just the variables, but also their mechanistic relations, right? So we're going to talk about mechanisms. So let's start, like every good philosophical introduction, with some quote, yeah? So by Pearl himself in this case, in the most recent book, the Book of Why, which again was for like a more broad, general audience. And it goes like this. So some tens of thousands of years ago, humans began to realize that certain things cause other things, and that tinkering with the former can change the latter. Yeah? So tinkering the cause will have an effect on the effect. And from this discovery came organized societies, then towns and cities, and eventually the science and technology-based civilization we enjoy today. All because we asked a simple question, why? And this is, I think, also a paragraph very early in the book, or maybe even on the first page. I would have to check. But it justifies also why he's saying why. Yeah, at least justifying in the sense that we have not covered how this now relates to this, but he's obviously saying that this relates to this, and so that's why he calls the book like that. Essentially, SCMs are models which talk about counterfactuals, and we're going to see that this is the richest class, which subsumes models, interventions, and observations. So to give a brief analogy on this, so if you consider actually mathematics, or like what then became known as computer science, which we studied today, which I also studied, and I was always wondering whether famous people like Einstein, Turing, Gödel, if they had computer science, would have chosen it as a major. But essentially, it's really that the notion of a computation, right, was only formalized in these early 20th century by the likes of Alan Turing, Kurt Gödel, and others, right? And yeah, modern computers are really a short-term consequence of a grander scale, if you think about it, because, well, we are in 21st century, and I don't know, we have smartwatches, we have phones, we have supercomputers everywhere, right? So yeah, good thing that before 1920s or something, we only had like a semi-formal notion of this, right? And then we formalize it, and boom, progress is made. And so this is kind of the hope, right? That essentially Pearl's formalism is a language for studying causes and effects and their relationships, in hope of a similar fate, right? That essentially, if we formalize this, if we have a language that smart people will then use it and develop things, and obviously the analogy here would be that causal AI, right? And causal AI, if we think that causality is really linked to things like generalization and so on and so forth, then yeah, that's the next way to go for AI, right? So again, on a philosophical note, there's this dichotomy between reality, so that what nature is, and in its essence, and what we observe, right? Like what we, through our eyes, through our nose, through our smell, all these different senses that we have, observe, right? Like all these empirical traces, which we usually call data. Yeah. I like to make also the analogy. I've seen it in some podcasts, I think, that for example, if you look at a male your mailbox on the desktop, the graphical user interface, right? Behind the hood, the reality is actually a different one, right? That like it's physical charges on and off, right? In complex hierarchies and so on and so forth. But what you only see is this interface, right? Like this is what we observe, and this is the mail, right? And it's just a totally different level of abstraction. And so this is kind of the play of this first point, right? Like this first challenge that we have. And then the second one is that actually we only have access to this data, right? So as Locke put it, when we observe data, we cannot so much as guess, much less know their manner of production, right? Like this distinction between production and what is actually there, right? Like whatever we see as data is the product of something generating this data. And this is kind of the philosophical backbone of this whole story. So how does Pearl solve this? Well, as this section's title suggests, representation of reality is through this structural causal model, which in this section we're going to define. And then the data of reality, which is implied by the STM, which will form this causal hierarchy, are all these different types of information, right? Factual information, hypothetical information after we change something, and retrospective information after we've seen something, we changed something in the past to get some alternative. And this is also called ladder of causation. So what we want to formalize is the following then. Yeah. So if you look at this graphic, right? So we have kind of argued that, you know, our perceived or in general reality adheres to causal mechanisms, right? That's what Pearl is saying. So there's, you know, causal mechanisms, but they are unobserved. That's why it's in the gray box. And they produce, however, this white box, the observed phenomena. And now we want to formalize, put in mathematical notation rigorously, consistently, what these boxes actually mean. And yeah, also XKCD comics like last time, I tried to find some fitting ones. Here's the one on philosophy. So you see someone sitting, at least behaviorally, nothing is happening. Yeah? Person is constantly sitting. Same in the second picture. And then in the third, it's, well, if the question of what it all means doesn't mean anything, why do I keep coming back to it? And then you see the colleagues, right? Like this could be in our lab, for instance. Yeah. You know, she's getting existential again. It's okay. I have a super soaker, right? Like wake you up from reality. Yeah. Okay. So what is an STM, right? So we're going to use, so I'm assuming now all these things we have seen in the past, right? Of course, you can always interrupt, give thoughts, questions, you know, impressions, whatever. If something is not clear, but this should really build up naturally now on the basics we have found last lecture. So an STM is first a set of variables, right? So it's this tuple, but it contains sets of variables. And what are these sets? So U and V. So U is a set of background variables, also called exogenous variable, exo in the sense of outside of the model. Why is it outside of the model, although it's in the model? Well, because it's not the variables which actually have a name, right? It's something we assume to exist, which is reasonable, but we don't specify them concretely. And yeah, like an Eselsbrück for this would be something like U for unnamed variables, right? Unmodeled variables. And then V is a set of endogenous, so within the system, that are determined by other model variables, right? So that's also a crucial distinction, right? These U's, they are not determined by other variables, they are set for themselves. Whereas these V's are set by UV variables. Now, we have a set of variables, or two sets of variables, and they are related mechanistically. So what does that mean? We have another set, but this set has now not variables in them, but functions, right? Functions which, you know, are these so-called structural equations or mechanisms. And each of these functions, for example, Fi, is a mapping from the respective domains. So let's say we have a variable X, like last week, you know, represents a fair coin flip. So it's either 1 or 0, heads or tails, right? So it's from these domains. And what specifically? It's from some exogenous parents, right? So some of these noise terms, unmodeled terms, but also from within the system, right? So some variables V, which are actually parents. So we denote by parents actually the ones which are functional arguments of these. And yeah, and so UI is obviously a subset or potentially equal to U, and PAI is all the V's without the one we are actually looking at. And essentially, we have this for each of the values, right? That F assigns, given the parents' values and given the exogenous terms, the unit terms, a value to this specific variable. And this happens for all of these variables, all our N variables in our SCM. Looks fairly general. Obviously, we can even go further beyond here and dissect this and what this really means, right? Like measurable spaces, Borel spaces, and so on and so forth. But this is not the focus of this, right? So we are taking this, for example, the notion of a parent. What does it actually really mean, right? But we are not digging that deep now here in this lecture today. And then the final ingredient. So we have seen sets of variables, we have seen the mechanistic relations, and uncertainty, right? So uncertainty is always an option, right? Because you can always have some delta distribution and then it's certain, then it's deterministic, but it's still a special case of an uncertainty, right? Where there's uncertainty equals 0. And this is depicted by this probability distribution, right? So probability distribution over these U's, over the domain of U's, right? And again, for example, we said, yeah, they are unnamed, so we don't know much about them. We just know they might exist. So how do we know the distributions? Well, you can make assumptions, right? You could say, okay, it's maybe distributed as a Gaussian. Yeah. So in that sense, it's close to what you know in machine learning commonly as noise. To give some more intuition, you can really also see it as a summary of the state of the world, which lies outside of what you're actually looking at, right? So for example, let's say two variables, x, y. One is, I don't know, a dice that I roll, and the other one is also a dice, a second dice. And these are the things I measure, right? I roll the dices, I record the numbers, for instance, right? I can derive anything, I can take their sum, I can divide them, I can do whatever I want. And these U's are essentially specifying everything that can happen so that it comes to an outcome, essentially, right? That you observe, for example, one die being something, yeah? And it really makes sense to see this kind of as a summary because it's everything else, right? Like everything we don't account for, but given that we know that there's things that we don't account for, but we cannot specify them exactly, we summarize them in some kind of distribution. Yeah, and also maybe one more thing to this term units, right? So you can also remember U as unit because it's really however the context is being set, these unknown terms, these summaries. And these are really, single elements of any population. So for example, if you're in a medical setting and we're studying, patients, then this would be a single patient actually, right? Or at least an equivalent class of patients which have exactly the same context, right? But if this is fine-grained, then it might actually capture the actual single individual. So what are the assumptions of this model M? So first of all, V and also its domain are finite. There's ways to also extend it to infinite variance, but generally, and also in most research, you'll consider only the finite examples. So for example, the set V could just be one variable V1. V1 could be a coin flip as we just had in the previous example. And then, the domain, the values would actually be 0 and 1, right? Representing heads and tails. Then there's two more less obvious assumptions. So one is M being recursive, and the other is M being Markovian, right? So both you could maybe guess based on last lecture, right? Because Markovian we've had and recursive, I guess, also tangentially. But let's explain. So let's dive first into recursive SEMs. So we say that an SEM is recursive if there exists this so-called temporal order, right? So a lot of critique, Pearl's causality framework usually gets from physicists, although Pearl is actually also a physicist by training himself, just like Bernard Chukov and others. Is that time is somehow missing, right? Time is not modeled. You can model time, but it's in this notion it's not explicit, and that's true. But then again, it's somewhat implicit, right? Like if you have a recursive SEM, which we'll see in a moment also what that equivalently means, then you always have this temporal order, right? So in your set of functions F, for any pair I choose, right? Like two, for the equation for computed X and the equation for computing Y, if say X causes Y, then I cannot compute Y before I've computed X. That's really what it's saying, right? Like that's really the intuition. You always have to compute what you can and then go to the next one, right? And if there's some kind of equivalence there, then you might choose between what you want to compute next, but you can never compute anything, which depends on the prior computation. And I guess that's trivial, right? But that's really what it's saying, right? And it's this fancy name. There's justifications, different ones for this name, but let's not dive into this now. More importantly, recursiveness implies acyclicity, right? Or it can be seen as the same thing here. So what we have seen last lecture with DAX, these directed acyclic graphs, that's essentially it, right? Like if the SEM has this a DAX structure, right? If it implies a DAX structure, it's recursive, right? But there's also another important or interesting implication, actually, that, you know, if an SEM is recursive, then what you have is that the exogenous terms, these units, these summaries of the nature of the world, right? They actually specify uniquely everything you're interested in, everything you give a name, right? So, for example, if I know exactly the state of the world and how it's going to play out, then I know, for example, that the first dice is going to roll like this and the other one like that, right? So any U formally seen fixes all variables V in the sense that for any set, which could be, you know, the whole set, we can write that the solution of running these structural equations will be Y when we use U as an input. So really, we can just see it as a function. So V is a function of U, and any subset of V, Y, is also a function of U, right? So as soon as I set the U, I get the values for the endogenous ones. And that's a property of recursive SEMs. Yes?
So we basically ignore all quantum processes to be the world.
Could you specify more?
Like quantum processes are really can't determine whether the photon is emitted in this second or a second later or whenever. So we can do that if we using a physical model where we allow quantum processes to be random, which they are.
So what are you trying to imply? Are you saying that essentially what you just described, that that this makes you think that this is not like a quantum process because the U fixes the V, but the U itself could still be, you know, dependent on the quantum process, right? So it's in there, right? Okay, so the next one. So we just saw recursive and then also Markovian. Markovian might fall a little bit simpler than the other one. So in general, we call recursive SEMs also semi-Markovian, right? Semi-Markovian. And now if the PU has a special structure such that for each of the single U's, it's just the factorization, right? Like they're independent. Then we actually also say that this SEM is proper Markovian, right? Like we just say Markovian, without the semi. And really what this tells you is, also in a different way, this is quite interesting. So we have seen this idea of a common cause, right? Like we have three variables, X, Y, and Z is causing both X and Y, but there's no relation, for example, between, you know, X and Y, right? It's really all due to the third variable. That's a confounder, right? Or actually it's only a confounder when there is an error, because and when, you know, the causal effect, which we're going to define, changes, but well, these are details. You just have to remember that essentially, if you don't have this property, right, then you have hidden confounders. So really what it's also telling you is that you don't know all the variables yet, which, you know, are somehow relevant. Yeah. This is interesting, right? This might seem also a little bit different now, again, from what we've seen last week from Markovian. So let's link back. Well, when we have a hidden confounder, then the distribution of what we observe is not Markov relative to the graph of M, right? So actually this cut out. So this was from prior version. But yeah, so I told you earlier that, you know, the SEM somehow implies a graph structure, right? This is what we denote by this GM. We're going to see this in some later lecture. And we said last week that, you know, if a distribution is Markov relative to a graph, right, the graph is an IMAP, right? So any d-separation will imply an dependence in the probability distribution. But if you have a hidden confounder, that's not the case. And that's why we also call this Markovian, right? So what we just saw now, right? Why this actually is a Markovianity property, right? So we have seen the SEM's assumptions are, you know, the finiteness, the recursiveness / acyclicity, and the Markovianity, right? That, you know, there's a factorization. Obviously, we can also work with semi-Markovian models. They are less nice, obviously, because they allow for more, you know, fooling on our end, yeah. But exactly, that's the thing we are looking at today. So let's make finally an example a bit more formal. So let's say we want to describe a game of chance, right, through some SEM M. Then we could do it as following. We could have two variables X and Y. We can say now, for simplicity, there's also two, you know, unmodeled terms, U1 and U2. They're going to have some kind of probability distribution, which we are going to specify in a moment. And we have the set F, which we are going to define as follows, right? So we say X is assigned the value of the sum of the two terms, and Y simply the difference. And what does this then mean? It actually means in words that M now represents a game of chance with two dice, where X represents the sum and Y represents the difference. Quite simple, right? This is because right here, C, UI is K, right? And this is 1/6 for 6 options, right? So it's a typical dice, right? 1 through 6. We roll the two dices, and now we record the value of the sums, right? And that's what this SCM now represents. So if you were to run this SCM now, you would get a distribution over all these different runs of, you know, having the two dice have certain values, right? For example, die 1 being, for example, 3, and dice 2 being, for example, 6 or something. Yeah. Okay, so this is now the bridge that we do. Essentially, we have seen now the representation of reality through an SCM. It consists of these 3 things, being sets of variables, their relations, and uncertainty measures. And they have certain assumptions. We can loosen these assumptions, but that makes life difficult, right? So we might not opt to that. And here in the following, we are now going to look at these Markovian SCMs mostly, which are cyclic. And yeah, we have seen an example. And now we want to see actually what I've been hinting at, data generation. So any question or any thoughts or something, anything you disagree with Pearl, right? Like, this is not me, this is Pearl, right? Like, I'm just presenting it. So anything which comes to mind maybe to this representational part. Yes.
I understood the different V's were just fixed parameters we input to the model as assumptions, right? So we have like U that are dependent on something previous or get set in the meantime. I took this from the side way in the beginning, like when you define the terms, and V was fixed, right?
So I mean, V is fixed and U is also fixed because you fix them, you assume them essentially, right?
Okay, so the definition or the way we get the different values of V is that we have different functions that get values of V from U, and that's the only way we get.
Yes.
Okay.
But you see now, for example, here, X is the, you know, the value X you get from the function Fx or F1, whatever you want to call it, which has as arguments U1 and U2, because it's the sum, right? It's a function of U1 and U2. Could also be a function of Y, right? So you know, that's the thing, right? Like, you're going to see more examples like these. That's actually what we then typically mean as causal, right? Like, if I were to draw this graph, then there's these two U terms, which we typically actually don't draw because they are, you know, they don't have a name. And we would have X and Y, those we typically draw, and there would be no arrow between these two. Why? Because Y does not appear here and X does not appear here, right? So there's no arrow to draw. Right? We're going to see this also in the next lecture on I think it was causal discovery then. So there we discuss all the graphical stuff. But that's really what's going on. So you have these functions, and these functions give you the V. And they use the V and the U to compute it. Right? And when I say the V's are computed also based on the V's, it obviously implies an order, right? You have to compute some V's and then some others. Yes.
And we don't have hidden co-founder.
This is the case, for example.
No, so U2 is depending on the.
Oh, so they they are yeah.
Does that mean that need to push U2 to be reset, or how?
No, you cannot do that. What that means is you have a hidden confounder. That's what it means, right? Because as soon as they are dependent, right, that's really just a hidden confounder on those. Yeah. What do you mean?
What if U2 is totally defined by U1?
If U2 is totally defined by U1, so I have a function which is not a structural equation, which computes.
You want to like distinguish between latent and Savina's random variables.
So Moritz is right in saying that, you know, when you, for example, U2 is a function, some kind of function of U1, right? you can do this, right? And what it would just mean is you discuss the relations, as Moritz says, of the latents, right? And now what was the question here?
Yeah.
Say U2 is a function of U1, okay?
What is the amplitude Jacobian? Does that mean to put U2 into V state?
You can never do that because, again, these V's are the ones which actually have the names, right? Like you could artificially come up with something, but it would not have any meaning, right? Like because you would have to invent a structural equation. And if you think about it from a graphical point of view or structure, right? Like I have X and Y now, and they depend both, right? It's this graph from last week, right? Like in this way from the U's. And now let's say this U is actually causing this one, then it's really just pointing like this, and then you have this. And you can treat those as one variable, actually, one latent variable, and that's a confounder again. Yeah. But cool questions. Yeah.
Example, what we actually observe in the real world.
This is what's coming now in section 2.
Okay.
Yes. Because this is now just a representation of reality, right?
Yeah.
Obviously, this represents, rolling dice. So, but the only variables that are named are X and Y. So what you would observe is not the single dices, but only the sum and the difference, right? It's like someone does the experiment for you, right? And then just gives you what he has written down, right? That's what's coming now. Cool, then maybe let's just jump to that actually. So section 2, causal models as data generators. So in statistics, the king actually, right, or the queen or whatever you want to call it, is actually the joint probability. Because using base rules, probability theory, we can derive anything. Yeah? That's why Yuda was fighting so long, because he was saying, well, there's conceptually some difference, correlation and causation, they are different and it's a thing, yeah? And he wanted to capture that. But statistics and probability theory didn't have any tools for doing that. It was just a joint probability. And what you're going to see now is actually that the SCMs create not just one, but infinitely many joint probabilities. So they stand on a meta level, one step above the king of statistics, right? And so that's why we say dethroned here. And let's dive more formally into this. So we saw the first type of information is kind of like factual information, right? There's often this analogy of seeing or just observing, right? And how is it defined? Well, if we have an SCMM, it defines a joint probability over all the variables with names, right? For example, X and Y in the previous example, such that for any subset, for example, if I just consider X or if I consider both, whatever, the value actually for them being some value Y here is defined as this term, which looks complicated at first, but it's really simple. It's really just a sum of all the nature terms, right? All these summary states of these units, right? Like all the units essentially and their probabilities, where we have this consistency, where essentially, if you use this unit, you can actually get the Y you're looking for, right? So this is the indicator function here now. This is 1 if, YU is actually Y and it's 0 otherwise. So we're going to look at examples in a second, but that's really just it, right? And you're just taking the sum of all these U's, right? Like essentially, if you have a table, you just identify the U's as you'll see later on, and just take how likely they are. And that's really what gives you this distribution. So let's actually do an example now. So let's take our SCM from before, right? So structural equations for X and Y, U1, U2. And we want to know, for example, the following joint probability. We want to know if we observe that, the sum of the two dice is 2 and the difference is 0, then what is the probability of that happening, right? Oops. The only compatible unit actually, which you will find is U1 being 1 and U2 being 1. Because if those two are 1, then here 1 plus 1 is 2, 1 minus 1 is 0, and nothing else. It's the only unit. And we know that a unit, because here 1 is 1 over 6, and they are independent. So this is just like in high school mathematics, it's 1 over 36. And so we have that the probability of this event is actually 1 over 36. Super simple. Now a bit more involved example, using a conditional, but again, derivable, right? So what if I've seen already that it's X equals 2, right? Like what if, as we were just saying, right? Someone gives me the sheet, but now they just give me 2. They just say X is 2, and I know X represents the sum, right? what does it tell me about, the difference? Difference actually being 0, right? Funnily enough, again, the only compatible one is 1 and 1, right? Because again, 2. But now this changes, right? So we know that this was 1/36, and this is actually just the same as over 2, because you can go over all these different differences. And then what you get is the following. We just divide over those, and what you get is 1. So when I know that the sum of my 2 dice is 2, then I automatically actually know that y must be 0, right? Because again, it was just this case, right? So if it's 2, I know the only combination which makes it 2 is first dice is 1, second dice is 1. And if I know that, then I know that 1 minus 1 is 0, right? So that's where it comes from. Now, to give a more involved example, right? Like it's always nice to see these very simple examples because they convey the conceptual, the foundational ideas, right? And I told you about how Yuda would say, I don't understand 5 variables, let alone 1,000, right? He surely understands more than 5, but let that be aside. We still want to, do this in practice, right? And if we work in a company, for example, or if we in a hospital, right? As for this medical example, it's a lot more tricky, right? It's a lot more involved. So how can we maybe model something, even on a very simple scale like this? And so we are going to do a bit more of an involved example now, after we have seen, how we can actually generate data and what the SCM is. So consider this medical example where we have the recovery from some disease, right? I'm not specifying anything. It's just abstracted example now, but we are trying to make the numbers look reasonable. For some patients with and without some symptoms, and with and without some treatment, right? This could be a drug prescribed by the doctor. Now we can represent, we will have just, 3 variables. So we'll say X is going to be the treatment, right? So let's say an aspirin or something. Y will be whether the patient feels better, will recover from the disease, right? Say, I don't know, has a cold or something. And Z could be a symptom, for example, running nose or something. Now we specify a lot more U's. We'll see in a minute what they mean, and obviously some structural equations. Let's go step by step. So we're going to say that the exogenous variables UR, they will represent whether a person has some certain natural resistance to a disease, right? Like say, they get a cold and then, developing something like a running nose because they have an immune system which is reactive, right, would be a natural thing. Yeah? And then let's say UX, UY, and UZ, those 3 exogenous terms, we'll say they exist, but we'll actually not really specify much, right? They are sources of variations which really lie outside the model, and we just assume something about maybe, in the limit how they might look like, yeah? Which is really general already in this case, right? Like UX, is again the thing with the treatment, right? And it could contain all kinds of information, right? Like it could contain, maybe the thing you expect, like if, I don't know, you have symptoms that the doctor would give you the drug, but it could also contain something like, my mom knows the mom of the doctor, right? And the doctor, now likes me more, so he gives me the drug, right? Like it can contain all these kinds of situations, right? And you can imagine already, like this is really creative, this is really boundless essentially. And so this is already very general, right? It's a lot more than this, what we specified here. And then finally, what we are saying is the general kind of, not finally, but like the general setting, right? That if someone has natural resistance, they're more likely to survive. Well, because of the natural resistance, the immune system is working well, regardless of whether they actually get the treatment or not. What we are also going to say is that when a person has a symptom, right? When you see the running nose, for instance, that the physician will actually the doctor will actually try to counter it by prescribing the drug, right? Also reasonable, I guess. And yeah, the final remark we just have is in words, if we treat resistant people though, they will actually overreact and, they will worsen their situations. So this is kind of the summary we have here of this model, right? We have treatments, we have recovery, we have the symptoms, and then we have all these hidden terms, right? Some natural resistance due to some genes, whatever, and all these other sources of variation. And generally, our system is such that, if you have the symptom, then you get the drug. If you're naturally resistant, you usually recover. If you're resistant, but you get the drug, although you essentially don't need it, then it might get worse. And this is the summary. So I've tried color coding this for you so that we can, dissect this in clusters, in groups. But these are really all the mechanisms now and also the distribution. So just quickly on the distributions, right? So for example, UR being 1, so someone having natural resistance, 1 out of 4 people, right? So it's more of a rare thing. Let's say UZ being 1 is for most people, as is UX, and UY is for a little less people. Why these are chosen like this, it's going to become apparent from this example, but it's not too important, right? These will mostly be these terms like most or whatever. So, for example, Z again was the symptom, where the symptom happens. Again, these ones here, or these I's, are indicator functions, right? So if this thing inside is actually true, then it's 1, and otherwise it's 0. And so what this now transcribes, UR1 and UZ1, is that natural resistance in most cases actually means an immune reaction. This is something we specified prior, and this is how it's being captured formally, right? Why? Because only a few people have, resistance, right? But most of those which actually have resistance, will have this immune reaction, so they'll have a symptom. Now for X, it's a bit more involved. It has these two terms. So we have first most people with symptoms, and a few without are actually getting treated, right? So X is the treatment. 1 is I get the treatment, I get the drug. And we see if you have symptoms, then 90% of these people with the symptoms will actually get it. Makes sense. If you don't have a symptom, right? Z is 0. Only a few are actually getting treated, right? Also makes sense, right? So you want to give it to some maybe where you are like in doubt, or where they might say like, oh, I don't have a symptom, but trust me, So, and then finally, the Y, it has these 3 terms now. It's the most involved now. As you see also, this is now the example we had from earlier, right? That here we now have the dependence of the V variables, right? So for example, Z depends only on the use, but X now depends on Z and use, and Y actually on X, Z and the use. Oh no, actually just X and the use. And what does this here mean? So X being 1 was getting the treatment, and UR1 being naturally resistant. So naturally resistant, people that were treated recover, and then most who were not treated plus a few non-resistant patients also recover. That's really what these equations are telling you here, right? We can always go in more detail, right? Like even after class or offline, right? So no worries. Also Mattermost, you can always ask questions to these examples. We can, do it live there. We have Latish in the chat box and everything, like it works nicely. But yeah, this is really the setup, right? So the thing we have all had in words now, we can formalize, right? So we have some reality, and now we have described it in terms of variables, so some background variables and their equations and how they relate to each other, right? Obviously, what's going to be very interesting in the lectures in part 2 of this course, which is on machine learning, right, and AI, how to actually learn this stuff, right? Because this is, this is the holy grail essentially, right? But we are discussing now, okay, if we know it's like this, what can we do, and so on and so forth. And so this table might look intimidating at first, but what it is really is just all the combinations, right? Because we look at binary variables here, although it's binary variables of more complex concepts, we have essentially these 4 U terms, and there's, 2 to the power of 4, so 16 different combinations. You see 0, 0, 1, 1, then 1, 0, 1, 1, 1, 0, 0, and so on and so forth. And they, because this is a recursive SEM, fix, right? The exo fix the endo. This was one of the properties. So these ones are just simply computed by these 16 different combinations. And now in the last column, you always see what is actually the probability, right? Numbers look crazy possibly, but very simple to calculate. How do we get them? Well, we have here again the probabilities of each of those independently, and they are independent. And or at least, this is what we assume. And you get the reverse because it's binary just by taking one minus the other. And then, so for example, the probability of UR, UZ, UX, and UY being all 0 would be, taking 0.05 0.75, 0.1, and 0.3, multiplying all together, and you get this number, which is, below 1%. And you can do all this together. All this would sum up to 1. These ones, for example, are very unlikely, but you see, for example, here's a heavy hitter with, almost 50%. So what this also kind of tells you is that, most situations are actually like this, right? Like that, someone is actually not naturally resistant, but that these sorts of variations are all triggered. Bless you. Okay, so now let's do another example where we actually calculate the quantity of interest. So we want to know now how likely, right? Like what is the probability for someone who has actually received treatment that they recovered, right? Like if you have had treatment, how likely it is that you had recovered. And expressed in probability theory, that's just simply this quantity here, Py equal 1, so recovery being 1, given that the patient was treated, x equal 1. We know this conditional we can just compute by taking the ratio of the joint and the marginal. And this, again, we know from our formula how to evaluate. We simply look at the consistent cases and take the probabilities, weigh them by their probabilities. So we look at all the U's in our previous table, right? In this table, we will look at all the U's now where x is 1 and y is 1 at the same time, and then also only where x is 1. And then just take all these values, sum them together, you get 0.25 here, 0.29 here, 74%. Okay. Easy, very cool, fun. Yeah. But, I also wrote some Python code for you because last time we had R, so I wrote some Python code. Yeah. It's really simple, as you can see. I mean, it's a couple of lines, also structurally redundant. I import, so this itertools package. I can just, take the list of the product function, takes multiple lists as input. That's really the Cartesian product. I import NumPy. I set the print options so that I get this stuff. And then, these I just encode, for example, here by hand, right? I went 2.5, and then the reverse one is 1 minus. For all of them, I collect them in an array. I concatenate those and then compute these combinations, right? Like all of these different ones. And really just, if I print this now in a data frame here, pretty with all these columns, that's what I get actually. So, pretty straightforward. Yeah.
Are there already some frameworks where you can just input each tuple of the SCM and then?
There is by now a couple, and we're going to see them also at latest in the coding session. We will have at least one coding session, right? There's a couple of libraries and frameworks, but for very different things. For example, this is now just the SCM representation part. I feel like here it's a bit more lacking, right? Like I think there's nothing nice, but don't quote me on that. Whereas, for example, the topic from next lecture or the one after, which is discovery and identification, effect identification, these ones have pretty strong libraries already, right? So things like do-why and all other kinds of ones. Come also in different languages and frameworks and stuff. A lot of things are obviously in R, but a lot of things by now are also in Python, right? So, and it's also a bit of a divide. I feel like causal discovery things are a lot more in Python than they are in R, for example. At least, the more modern stuff is that, not on conditional independence test based and stuff. Things which are more closely in nature to statistics, I guess, are the ones which are more in R, which seems natural. Cool. Now I want to discuss implications, right? Because this is now, where we're always tempted. Yeah. So we saw 74%, right? And now we can look in the same way at a different number. I've just computed this now for you here already. 32% if you didn't have the treatment, the likelihood of recovering, right? You would think that actually treatment should have a positive effect, right? Because more than chance, right? Like 74% actually recovered when they had the treatment, right? But is that the right implication, right? And knowing from the XKCD comic on base rule, the answer is no. So we're going to see this now. But yeah, first another comic, health data. So let's start at the left again. I'm taking a look at your numbers, says the doctor, and it doesn't look good to the patient. You have a lot of measurements, quite a few variables. Now the patient says, oh, is that bad? And then the doctor says, variables are the #1 risk factor for outcomes. The past is a big contributor to the future. Well, she's not true, yeah. And then the patient knows, well, has listened to this course. Isn't that just causality? And then the doctor just says like, well, causality is the leading cause of death in this country. Yeah. So yeah, what are my odds? And now the final question, yeah, well, do you have family history? History of what? Yeah, just in general, yes or no, right? So you know, we have to be careful with our implications. We have to know what we talk about, and that's why we do this course. So yeah, health data, I think was quite fitting, especially this one. When I saw this, it was quite funny. Okay, so now I want to talk about where it really becomes causal, right? So I want to talk about manipulating structural causal models. So let again M be some causal model. X is a set of variables in V. Small x is again a particular realization. And now we say this submodel written with M and then the subscript X is the following causal model where everything is the same as with M, just that these structural equations, the set has changed. And there's a very particular way it has changed. This is also known as a hard intervention, that essentially you have all the functions from before, right? All the ones which are not manipulated. And now this new function for those which are manipulated, which are being set to exactly that value. So really what this tells you is if we have our x and y from before, and now I say I want to set x to value 2, now I just replace the computation of x, which was previously, you know, u1 plus u2, and set it to 2. Yeah. To make the analogy to, you know, someone just, you know, rolling the dice and then writing it down and giving it to you, it's essentially someone, a middleman or the person itself manipulating, right? They just, although, you know, the dice were say 1 and 1, so x should have been 2 and y should have been 0, the person writes x is equal to 3, right? And y is still 0, right? Yeah, that would be an example here. And so where do we go from here? So one more important notation and now a key concept to define is this so-called potential response, also known as potential outcome. You're going to see why I do this here, right? So usually I would do something else, do calculus, do operator. And I'm not going to do this, and you're going to see why, because we are going to do it the right way now. No? So let x and y be two sets of variables in V, just as before with just x, and u is a unit. We have seen earlier that, you know, u determines all the endogenous variables by, you know, I fix the u and now I can compute everything with the equations. I can also do this when I have these interventions. I can also do this when, you know, I manipulate the SEM. So what I'm saying is that the potential response is this object, which is a function of u, and it's the solution for y if the set of equations was not f, but f subscript x, right? And that's all with respect to some m, right? M gives the original f, and now I manipulate this x, right? So technically what it really is, it's a shorthand for this here, which is convoluted, so we don't write it, but it's really the y in the new manipulated model where I, you know, set the x to some value, and now, you know, a function of u. And yeah, to bridge this to our example from before, you know, this could be the recovery of the patient u. U is, again, in this case, actually any single patient or all patients which have same characteristics when actually being treated, right? So you force the person to have the treatment, and now you look at whether they recovered or not. And just a quick side note, right? So you can also just write yx, for example. That's actually what happens in this alternative framework, which was proven equivalent, but which other people have questioned, where they look at potential outcomes in econometrics and related fields. There they usually treat this thing as a random variable, and that's the key distinction here. Yeah? So the random variable would be some kind of, you know, average recovery had everyone gotten the treatment, right? Like if a doctor came and just shoved it down the mouth of everyone, you know, the drug, that would be this thing, right? But this thing is really a function, right? A function of any patient. It tells you for any patient what it would have been. Yeah? So, and why did we define this? Because actually we can now consistently define valuation essentially across all levels, as you see, but now for the second level, which is this hypothetical information, this doing, as we refer to, right? Because again, doctor shoving a drug down your mouth, that's him doing something or her, right? And yeah, so this is really the formula from before, but I've highlighted in red now what changes. And it's just one thing. It's just that this subscript x, actually, I could have just had the red x here. Yeah? It's just the subscript coming here, which means now we consider, you know, the manipulated model from M. Yeah. But now, interestingly, because you choose these x, right? This is an intervention, you know. Like, again, the person who was actually giving you the sheet of paper after running the experiments, right? They manipulated, right? So instead of writing 2, they wrote 3, but they could have also written 4 and 5 and 6 and so on, yeah? Anything, yeah? They could have written Bob there, which wouldn't make any sense. It would not actually be allowed because it's not the domain, but, you know, if the domain was general enough, they could do it, right? And because there's essentially infinitely many of those interventions, right? Or, well, depends on a specific specification, but, you know, could be infinitely many. You actually have a family now. So what we saw earlier, level 1, was just the joint distribution. This is all you know from statistics, not different. But here, this is now different because you change something actively in the model, which you assume, which you expect. And actually, it generates an infinite number of, potentially infinite number of distributions, which all belong to some kind of family because they are derived from M. And we can capture this by the simple formula, right? So again, I just look at all the U's in the model where X was manipulated, such that Y ends up being the value I expect, and just weigh it by its probability of occurring. And so, as I've already hinted, this is the first causal quantity, and the word causal now is justified in the interventional sense, right? In the manipulative sense, right? That, you know, given our initial philosophical standpoint, that any variation of Y that we see will actually be due to tinkering, due to change, as Yuda put it, right, in X. And so that's why this is already causal, right? Like, because you change it, right? And you observe what's happening there. So again, to also reference our example here with the 2 dice, if we report for whatever reason, for example, as we said, you know, that the sum is 2, then it would look like this. This would be the new structural equation. X is just constantly always 2, yeah? But Y is still the difference. Then we see that Py equals 0 is the same as in the manipulated model where X was 2, because, well, Y does not depend on the computation, right? It does not depend computationally on X, right? So these quantities are the same. And if this is actually the same, then that's what we mean when we say X has no causal effect of Y, right? Like, changing X doesn't change Y, well, then there's no causal effect, although you change, right? It's not just the change itself, it's what the change does. So returning now to our more involved example, right, with the medical stuff. So this is going to be our running example here. So let's say, you know, public health officials, right? I mean, we have seen this in the pandemic, right? That, you know, COVID came and vaccines and so on and so forth, even if there was, at least not in Germany, anything by law or something, right? You know, society and everything, there's pressure. And so say they actually enforce it, right? Like, it's, I don't know, maybe a very big country, which is, you know, ruled by some communist party or something, yeah. But, you know, enforces treatment, yeah, to all patients with, you know, disease, regardless of whether they actually show symptoms or not, right? Like, the doctor really comes and shoves down the throat, you know, to everyone who actually has the disease, whether they have a runny nose or not. Technically, we just take from before, so everything in black is just copied, right? But what we see now here, X is equal to 1, right? X is constantly being set to 1. It's a law now, and we, you know, assume here now that the law is being kept. Now, there's downstream effects, right? In our temporal order, right? Things which depend on X, right, will change naturally, right? That's what we mean by a causal effect. And in our medical examples, this is actually the case. So this is the structural equation from before, and I've just put out of the bracket the important part, which is this X1 and UR1. So someone being naturally resistant and someone getting the treatment. This now all collapses to just whether the person is naturally resistant, right? Why was this again? Let me just think. Does anyone know? Again, my cognitive level today. Oh yeah, exactly. So thanks for reminding me. So so X1 means they've gotten the treatment, right? But because we know now everyone has to take the treatment, right? So everyone would have taken the treatment, and the other terms, they were just where treatment is 0, but they're inconsistent now because everyone gets the treatment. So really, it just boils down to now whether they are resistant or not, right? So this is what happens here. That's how we collapse this equation. Okay, so now let's actually look at an example of doing an intervention, right? Computing something interventionally speaking, right? So we want to know how likely it is, what is the probability for someone to recover if we actually give them the treatment. So it's not like we look at people who have gotten the treatment. No, we actually give someone a treatment, yeah? And so we denote it as this. So probability of y in the world where x is 1 being 1. And now we just use our formula from before. Here we just have to check this one, nothing else. And we saw now that y in this modified model is just a question of whether ur is 1. And that's just 25% because, you know, we specified this earlier. And so now we can actually do the reverse as well, right? Like we can say like, okay, I force everyone not to take the drug, right? Like I force people to stay away from the drug. It's 40%. So now we have a different kind of conclusion, right? Like if you compare these two numbers and with the numbers from before we had something over 70% and we had for you know the recovery and we had 30 or something percent for not recovering. But here's the reverse. We have 25% of recovering, so just every fourth person when they get the treatment. But 40% more people actually if they don't get the treatment. So here we would actually think that it's better not taking the treatment, right? Also, to just highlight again with some Python code, right? Like how this would look like, yeah? So essentially, we just have to get this set, yeah? So all the use where this equation is satisfied. And in our table, you know, you get this table by modifying the model, right? So this is a bit different from the previous table in that, you know, x is forced to being 1, and now y, you know, in this case follows actually completely. But you still have the PUs, right? And you just take now rows 9 to 16. So all of those. If you count all of these together, then what you get is this number. And yeah, just computationally, right? Like we just take the sum. For example, this here our data frame. We look at the rows, for instance. We look now at the distribution value. This is always the same here. And then just take the sum, right? And this is what you see here. So another comic now on interventions or surgery. You can also consider this to be a surgery. You are a surgeon on the variables, yeah? So on the left, it starts with, while you are doing the surgery, can you also implant this in my arm? So some kind of object, right? Looks like hardware. And then the doctor looks closely and sees, well, a USB port, huh? Well, just wire up to some nerves, right? And then the doctor, you know, already anticipating, predicting what the person might think is saying, like, this won't let your brain control USB devices, you know? And then, yeah, sure, I just want the hardware, right? And now here's the crux, right? So the rest is software. I'm sure there will be a project to patch together support eventually. Ah, you're a Linux user, yeah? Yeah, I know. So yeah, surgery, in this case, it's really, it's I guess less about causality, just about the fact that, you know, you're manipulating a system, even if, I mean, you know, people can have crazy requests. Okay, now finally, so I know this is a bit more dense. It's also the longest section. The last one is going to be shorter, but we are trying to bring this home. Retrospective information. So we saw factual information, what we refer to as seeing. We saw hypothetical information, right? Like if I intervene something, if I ask, you know, what would have been, then that's doing something actively, right? And now retrospective information, where we will somehow combine the two previously to have something like imagining, right? Like retrospection, right? Like reflecting, you know, on one's decisions, going back and choosing an alternate decision and thinking about where that would have led, right? Super exciting stuff. Like when I was a student and heard this for the first time, I was like, wow. And there's this famous 3-step procedure by Pearl, right? So we observe some factual world E. That's kind of the prerequisite. So it's essentially updating of a prior. That's really what's happening. That's the key difference to interventions, at least in this procedure. And so in step 1, we want to explain the past. So let's imagine, right? Like this always comes to my mind. I guess it haunts me, right? But like when I was a student, so I live in Frankfurt, and then I was traveling back from Darmstadt to Frankfurt, and I was coming more late than usual, right? I have my bike at the station, and I came back, and it was really dark. It was winter, and it was raining like crazy as well. And then I get there, and my bike was not there. And I was like, well, right there. I check everything, and then what I find is, you know, my lock. Yeah, was someone cut it, stole my bike, yeah? And the first thing I thought, damn it, if I just came like 1 or 2 hours earlier, maybe, you know, then my bike would have not gotten stolen. Yeah. It was less so the bike itself, because it was not that good of a bike, but it was actually something I inherited from my dad, essentially. So I was like, it has personal value. Yeah, whatever. And what we are trying to do here now is explain the past, right? So we want to know. So I observe that I come there and my bike is not there. And now I want to observe, like, I want to reason about the background factors, all these things. For example, one of the background factors would be that, you know, there was a thief around on that day, right? Looking for bikes, you know, which were blue in color. I don't know. Yeah. That would be one background factor. And given my evidence, this is more likely now, right? I mean, if my bike was not stolen, then I would not have any reason to conclude that there were thieves on that day, right? So that's what is happening here. So I have observed my bike is stolen. I'm going back to the past, right? And I'm updating my prior on PU with this evidence, right? So just briefly, I'm going to denote this by this notation. And now step 2 is very simple, right? Like in my head, I was bending the course of history, right? Like I was saying like, okay, me not arriving late, me arriving early. How would have that changed given the fact that there were thieves on that day, right? Maybe the thieves came only at like, I don't know, 7 p.m., right? And I arrived at, I don't know, 9 p.m. So if I came at 6 p.m., all would have been good, right? And that's what we do in the final step, right? We just use our modified model where we have this other prior, these other U probabilities essentially. And that's what we do. That's what a counterfactual is. It's clearly distinct conceptually from the interventions. It uses interventions in the second and third step essentially, right? But adds this extra step of having some prior evidence. So I want to make an example with now our running example again, and less hurtful with my bike. So consider patients that, you know, did not receive treatment and did not recover. So X0, Y0. We want to know whether these patients would have recovered if they had gotten the treatment actually, right? So we know this, and now we ask again this question, right? We have asked this before, but we know this now. We want to incorporate this in here. Yeah? So again, this is a question about a world which is not really existent. The factual world is this, and I'm asking now about a counter to the fact, a counterfactual world. Yeah? And one essence of these counterfactuals, which Dave also told you in the first lecture, was you cannot really sample from distribution. Like I can unfortunately not go back in time and get my bike back. Yeah, and that's the essence, right? So let's do the number game. So here I've computed for you for all these different computations. Now the updated evidence. How do we get it? So we take PU from before, we take our evidence, we look at, you know, the case x0, y1, y0. And then, for example, if we look at, for example, UR. UR being 0, while x is 0 and y is 0, is just the sum of, you know, all the PUs in this case. And now that would be the joint. So we divide it by this to then get actually the conditional. And that's what we get then there. Yeah. And now in step 2 and 3, we have now this other SCM, right? Like we do the same game as before, the same computation. It's again rows 9 to 16. It's just now that we have different numbers here. And what you get is here, about 2%. Here, just the code. So again, to show, right? Like what I'm doing here is the 3-step procedure. So we need to update the prior. This is our evidence. The evidence is consistent with rows 4, 8, and 11, and 13. And now what I just do is I look at UR equal 1, for example, within those rows, and the only ones consistent are 11 and 3, and then 4, 8 for the others. I do this for all the variables, and then this below is just the same computation as before. And what it gives you then is this circa about approximately 2% following our counterfactual analysis. And so what it tells you is that even if we had given the treatment to everyone who did not survive, right? Like these people did not survive, unfortunately, and they didn't get any treatment. And now we were asking, okay, but like, would have the treatment helped, right? The answer is, I guess, at least for your conscience, it's good, right? Is that only 2% would have actually recovered, right? Like it would have helped, but just very, very few, right? So you might don't bite yourself too much at night when sleeping, yeah? So yeah, the drug would not have led to recovery. Yeah? Now looking at a different quantity, for example, the ones which did actually recover when they didn't get a treatment, what would have had happened if they actually had gotten a treatment, right? interestingly, here it's about 11%. So what this tells us is that the vast majority, almost 90% of the people who recovered without treatment would have not recovered if instead they had gotten the treatment. So actually, for these cases, it was kind of good that we didn't give them the treatment. Because remember from our medical example, we had, natural resistance in few people. And these people, if they actually got treatment, they got worse, right? So they definitely fall into this example. Finally, what I want to conclude with now is the words formulation. So what you see now here on the slide is an evaluation scheme, which is a lot more similar. Well, it's pretty much the same up to the red part here from what we've seen before, right? Like if you remember the factual, this level 1, the associations, we just had, y given the u. Then with the doing, we added the subscript here. And now with counterfactuals, we are actually considering just multiple of those. It's just a copy of those. So essentially, you can see interventions as a special case where there's just one such set. But counterfactuals are multiple of these sets, right? And that's why we refer to them as words. And why did I present it like this? Because this is actually a generalization of what we've seen before now. So the 3-step procedure is very intuitive that Perl presents, but it sometimes makes it challenging, to understand the exact relations. But this formulation makes it very clear. Yeah, it might be less intuitive at first with the words, but we can easily verify, that, for example, what we have just seen now is a special case of this formulation. Yeah, and this formulation just simplifies it conceptually a lot, right? There's just one step, not 3 steps. Yeah. So let's do a calculation with this. Again, we have seen that people have not recovered and they didn't get the treatment. What if they had, and how likely would it have been that they recovered? Via the 3-step procedure, we had about 2%. Now we can do all of this in one step, essentially. So we get this conditional by just taking the joint and then the ratio with this other joint. And then we replace now with the equation from the last slide. So we just look at all these u's which are consistent with this and all the u's which are consistent with this. And then we get these 2 numbers. And well, it's again 2%. So we see it's the same numbers, but a different way, a way which is very consistent with everything we've seen so far, actually. So that's why I like for you to remember this as the key concept and the 3-step procedure on the more intuitive level. And you see also here now, right? And what justifies this, right? Like these are different numbers, but we get to the same result. How can they be the same? Well, here we consider essentially all of these settings at the same time, all these different worlds simultaneously, and the use which can account for all of those, right? But in the 3-step procedure, if you remember, we looked at the updated U given our evidence. So in this 1-step procedure, we just take the U, but now we consider the U which is consistent with everything at once. Whereas here, we updated U first with the evidence, then modified, then computed. Again, simple code here, right? So what you take here now is an intersection, really. So we had these rows like, what was it, 4, 8, 11, 13, whatever. And now you look at y given the intervention x equals 1, and then it's only rows 11 and 13. This by this other probability, and you get the same result, about 2%. And now the famous do operator, right? So now the thing we have seen a lot of times, people who have attended the seminar know this already, or if you remember from the first lecture, this famous do operator is now really just a notational convenience, actually, right? Like it's not that distinct, or it's actually not even necessary, right? Like a lot of people in statistics were like, oh, why do we need a new operator? And then it's called like do. It's like a computer sciencey, geeky thing, nerdy thing to do, yeah? Yeah, pun intended. And here's the relation now. So we use this potential response notation, and it captures interventions, counterfactuals, everything really nicely, very simple. But if we want to write do, then what we usually just want to emphasize is that it's just layer 2, right? It's just intervention. Like we do an intervention, what's the variable? If we want to talk about counterfactuals, then do gets really messy. So that's why we choose this one. And so to still make use of the do, we can use it to only, talk about interventions. and the other one counterfactuals. I personally, I'd prefer actually just using this one because it's consistent and it, you know, does not add more notational complexity. But formally, this is the equation which satisfies everything, right? Like you could do it, but it would like look like this, right? That's why it's messy. So if you have a do essentially behind your in your conditioning set, so to say, then this applies to everything under the hood. So both y and z. And written differently again, you can see it would be something like this. So it's like the do is actually accounting for everything, right? Like I do the intervention now, look at these ones. Yeah. So to summarize the section really, you remember we had the gray box and the white box. We have come a long way now, and we have white boxed, well, the gray box and also the white box. It's more white than before. Yeah? And we understand now that you know, the causal mechanisms, right? Like these structural equations, the structural causal model, that this is what represents reality, but we cannot observe it. But what we can observe is what we get when, you know, you run the SEM, when nature runs the SEM, which is these various distinct distributions, you know, factual information, hypothetical interventions, and counterfactual retrospective information. And as you can see, I'm already pointing to our final section of today, which is definitely shorter than this one, which is L1, L2, L3. So we seem to kind of classify those also like in a more formal sense now, and this is what we're going to do next. So before moving on, anything to, you know, all, yeah.
We can possibly have like multiple outcomes of X or multiple versions of X. We can just sum over them. Why should we use the do operator to apply a different version? Maybe it's
yes. So I think what you're referring to is essentially what about the concrete realizations? And that's true, right? Like especially in the counterfactual formulation, you have these different worlds, right? And they're all restricted. And you can just consider different values for X. And actually, this is what Perl also does. There's a lot of work. We are not covering this here today, but probability of necessity, sufficiency, probability of necessity and sufficiency, right? Like PNS is defined as a quantity P of Y under the intervention X, and Y prime, some other Y, under some other intervention X prime. What's the joint probability, right? And it's related to the necessity and sufficiency of a cause, right? Like it has some meaning, yeah? And yeah, that's correct. Yeah.
Actually, maybe probably explain the difference again between the conditional probability and intervention. I think that
so let's go back. This is important to capture, but you know, this will become clear. I think this is one of the things that most people struggle with, which is why I chose to do it this way, because I think it's easiest to show. We'll have opportunity also in the next lecture on causal discovery and things to see how it's different also on effects. So all throughout, and this is because your brain is also now having new connections, trying to make sense of it, right? But let me just jump back to some slide where we just do some intervention. So formally, it's just this, right? And now your question is really, okay, when is this? So there is cases where conditioning and intervening is the same, right? For example, if you have just X and Y, and say X is causing Y. For example, you know, X is just treatment again, and Y is the recovery. And if you take treatment, you recover, if not, not, right? Then conditioning on X being 1 and intervening, so putting X to 1 is the same. Like in both cases, you know, if you give them the drug or have the group that had the drug, it will recover, right? But in reality, it's not the case, right? Why? Because you have a confounder. As soon as you have a confounder, intervention and conditioning are not the same. So the confounder could be your symptoms, and say you have big symptoms. So the doctor is prescribing you the drug, but big symptoms also mean you are less likely to survive, right? Like that's why it's like a triangle relation, yeah? If you have small symptoms, right, like bad or no symptoms, you're not getting the drug, but you're also more likely to survive, right? And so you have this, you know, backdoor information which can flow. And so if you intervene now, you're really discarding all the connections to the symptoms. Like the doctor, as I said, will give, you know, the drug to someone who has big symptoms. So if you look at the group of all the people who have had the treatment, they are people who have bad symptoms. But now if I intervene, someone who has no symptoms, who would usually not get the drug, now gets the drug because, you know, it's decoupled, right? It's also the whole thing of, you know, the A/B testing, these randomized control trial, right? Like you have a control group, you have the test group, right? You give some people the drug, some others not, but you do it randomly. Why do it randomly? Because it essentially decouples any connection from before, right? Like there can be no other reason, right? And that's what intervention tells you. And so just to go back to the calculation, just to see here, it's this thing, right? There's essentially, the table changes, right? The equations change. So fx is different than f, right? Like here, the regular f was just this thing, yeah? Where y was this, right? But now in fx, it's just this thing, yeah? And obviously it's going to be different. And it's all these things that I was saying. But again, on a broad level, conditioning in the intervened SEM is the same as intervening in the as intervening in the original SEM. That's the relation, right? And obviously there's cases where these SEM, right, they have no confounding. Very simple cases, rare cases, but you know, conceptually we can discuss them, and then they would be the same. But usually that's not the case. But also good question, because you perfectly link now the bridge to the next topic, which is the causal hierarchy theorem. Because what you were just asking was, what is the difference between you know, associational and interventional, right? Like, what is really the difference, right? Because if there was no difference, then all this bullshit doesn't make any sense. But I'm going to show you that it's not bullshit, because there is a borderline, right? And this is what this causal hierarchy theorem does. It really tells you that one level which sits above another level is always a prerequisite, you know? So it's really more complex. There's like, you know, there's models which will agree on the observational stuff, but will disagree on the interventional, and even more so on the counterfactual, right? So it's more rich. And now we want to finally, the last 10 minutes, 10, 15 minutes, we want to use to capture this, at least as much as we can, right? So again, we are reassuring that causal inference actually is a sensible concept. I mean, we have seen, you know, the definitions kind of make sense, but is that really so? So just as a brief summary again, yeah. So we have L1, L2, L3. This is now the symbols which we are going to use to denote any of these quantities. And you see, for example, here's the do operator. Here we have the potential response with, you know, colliding X and Y, for example. Imagining doing C, yeah. Obviously, as an analogy, they are different, right? And, you know, the questions they answer are also different, right? Like, you know, what does a symptom tell us about a disease? That's different of, you know, something like, if I take an aspirin, will my headache go away? And that's even different of asking the question, well, my headache went away, but was it really the aspirin, right? Something like attribution, essentially. In machine learning, as we're going to see in part 2 of this course, it's going to be, you know, this is more like classical machine learning, and this is more reinforcement learning. So it's not like it's not being done. It's just like not formalized rigorously, which is what we are trying to do. So if you look in the book of Y, this might be, I think also Dave used this. This is probably one of the most popular ways of discussing the ladder. It's this nice illustration. And yeah. Yes, sure.
What actions are also reinforcement learning, or what is in top row?
So top row is empty.
Okay.
Right. So I'm not going to spoil anything much, right? But obviously there's analogies. Obviously machine learning, we can also discuss counterfactuals, but they are the hardest and the highest for a reason, right? Like we wouldn't put Einstein there if there's, you know, like no reason for it, yeah? But yeah, going back now to this illustration, this was like Pearl and Mackenzie's book, very nice illustration, which shows you a ladder. A ladder naturally implies that, you know, I have to take one step before I can go to the other, yeah? You cannot, well, you can maybe jump if you're one of these crazy Japanese firefighters, but say, yeah, it's building upon this. And then, you know, at rung 1, we see an owl and a robot, right? Clearly implying animals and, you know, current AI systems. And they're just at rung 1. There's 2 more. Rung 2, which is, as we said, the first causal, right? Because we changed stuff. We have, you know, our human ancestors and babies depicted, toddlers, right? Like they go around, they are big enough to stand up, they push something down, yeah, and then, oh, physics, yeah. And, you know, and then at rung 3, we see Albert Einstein. Well, Albert Einstein, I guess, didn't invent the skyscrapers and, you know, the laptop, but that's this depiction here, right? Like this is the book of why led to these nice technology-based civilizations. Why? Because we can, attribute, we can retrospect, we can think of alternatives. Yeah? Okay, but really, the question we are now trying to answer in this section briefly is, well, this would be a whole lecture on its own, but I wanted to give it to you, right? Because it's really, justifying this whole section, this whole endeavor, this whole course, right, on a foundational level. Does it really imply this question mark? Is it a letter actually, right? Like we depict it as a letter, but is it actually? Is it more strictly contained? Yeah. So let's look on a more technical note, again, on these rungs. At least here we can see a difference, right? A very clear difference. So this goes back now also to your question again, right? So observation, intervention, counterfactual, L1 to L3, and there's 3 dimensions. Hey, so we look at the external state. So again, our summary of nature and everything, PU. We transform it, we run it through our equations. It's a simulation of our SEM. And then we get some observations, right? Like again, with the medical examples, all the different patient situations and so on. Yeah? But now with the interventions, there's a slight twist, right? Like we modify the system, right? Like these are not the same equations anymore. And so they don't induce the same distribution anymore. Yeah? Well, not necessarily. Yeah? And finally, on the counterfactuals, in the many world interpretations that we have seen, we see that, we can have different interventions, right? Like we can intervene on W, we can intervene on Z, we can look at different subsets in their joints, right? Like it's a combination, it's a conjunction of those. So quite clearly here, we have the hunch, also on a conceptual note, as we have seen, that there is a difference, yeah? But we are going to use logic now to actually formalize this and formulate this and possibly capture this, right? We didn't cover any backgrounds in logic now, right? I'm going to try to keep this simple now, but it's nothing much, and nothing not to be expected, I guess, from computer scientists, and especially math students. So we'll formulate, these probability alpha terms, right? And they should become more complex when we actually go up this hierarchy, right? While having a sensible formalization. So let V, again, be our variables, right? From our SEM, X, Y, Z are some subsets. And now we are going to depict by these L terms, Li, L1, 2, 3, Boolean combinations, essentially, of inequalities between these polynomials, right? Why inequalities, right? I mean, if we have the conjunction of vice versa, we can capture equalities, right? So we have all in there. They're more general. And they are all over these terms, right? So they are going to be part of these formal languages, right? So what we are doing now is syntax, right? Like just the symbols, right? I'm not going to be overly rigorous on this one. So for example, the P, I'm just going to overload and reuse, right? But now we're just talking about symbols. They don't have any meaning for the moment, right? But we are giving them semantics in a moment. So language L1, briefly. So L1 will just be all these terms of this form, right? That encodes some probability that, some set of variables Y will take value Y, little y. And how do we do it? We'll have a grammar. So it's just simple. We have the sum, the product, negation, and a terminal set. And terminal set will be all these base probabilities, things like, Px equals 1, observing that someone got the treatment. This we can do with a propositional language. So we just define it as, some value instantiation, for example, x equals 1. The negation, right? So x not being equal 1. And conjunctions, right? Like joint probabilities, x equal 0, y equals 0, and so on. We just set this as this, and then L1 is really then, if we take this, combine it together, and we get, these inequalities, the negation, the conjunction of these inequalities. So it's Boolean combinations of these inequalities of these base probability terms. Again, they're all symbols. The P here is just a symbol for the moment. Let's do a simpler derivation. So what we see here now, stepwise substitution. Here I'm doing a little bit of a jump. But what you see is, for example, I start with this inequality TT. Then I have a product on the left side. I replace, right? So, I just make use of this. So T can be this one. And then, I replace this outer T with, the sum. And now if I choose the P terms, right? And I choose as the following. So P1, which will symbolize, certainty. Pxx and yy and pxx. And what will this essentially mean? This will be a shorthand for this, right? So imagine I take this over to this side, and I take this one over here, then really I have this quantity, right? Like if you take the natural intuitive meaning now on a semantic level. So really we can encode any kind of conditional probability statement with this framework. And this is for L1. So now to move to L2, to our hypothetical case, we want to have these potential responses, right? Like we want to have the modified situations where x was set to some value little x. Yeah? We're going to reuse the grammar. So we are, building this up modularly. So it's getting more complex only in the sense that, we build on top. Grammar T, terminal set T. And now we have this conditional language. It's going to be a bit different now from notation. This is now what's going to highlight what is syntax and what's semantics. Essentially, our L intervention, int, is going to be always in these brackets, and L prop is what we had from L1. And when we do this, so L int is just defined as, well, 1, V equals V, or just a conjunction. And then, this is just the same game as before. If we do an example iteration now here, what we arrive at is, for example, the following. So we could again start with the inequality. We replace with these terms. And I had these epsilon here as different placeholders. And now epsilon 1 could be, for example, the intervention x being set to x, little x. And epsilon 2 could be y being little y. And E3, epsilon 3 could be 0, right? Like the never happening event, right? And we're just now asking, well, this would be true, right? If there's actually a causal effect, right? Like if the intervention is having y be little y is greater than 0, greater equals 0, then this will be true, right? And so now here I'm already doing the semantics, but let me just briefly, before we can actually do the proper connection, have L3, right? So we just had this condition, we just wrote them in brackets, they should then translate to our interventions. And now we're just reusing again everything from before, but we are taking combinations, right? And so how does it look? So this L full will just be L full and the conjunction of it. And that's actually all that you need. That's a simple thing. It's just propositional in this case. So essentially all these things as before, but now we can take combinations. And remember, this is one single world, right? And a single world is a special case of multiple worlds. And multiple worlds are counterfactuals. So this is what's happening here. And now I want to just, equate syntax and semantics formally. So again, our SCM, I write down again, exogenous, endogenous, structural equations, and our probability measure. And now if we have, so this is now the interpretation for this SCM of what the symbol means, right? So here the P epsilon is a symbol from our language from before. And it actually means, like the interpretation of it is simply the probability of this S interpretation of the epsilon, right? So here you have now the equating of the syntax symbol P with actually the probability as we know it intuitively, as we have calculated this whole lecture today. And now the S, what is the S? Well, makes sense now. It's all the exogenous terms. Again, it's the sum, right? It's all the U terms where the structural equations of M with said U term would actually prove this epsilon, right? Which would actually model this epsilon. And so naturally, what you get are these kind of things where we don't have to go through detail now here, but if a model models, for example, some certain inequality, then this is exactly true when the inequality holds for whatever the interpretations of these single terms, which will always be some probabilities, right? So it's really just the intuitive level, right? Like if you couldn't follow here now, it's not even that important, right? It's just a formal thing to do now in logic, right? To equate syntax and semantics. And why? Because now we can actually formally define the Pearl's causal hierarchy, right? Like we have had all this intuition. And remember, in this section, we try to answer now whether the hierarchy actually makes sense, right? Like conceptually it kind of does, but is there a proof? And so M is again our fully specified SCM. And the collection now, like all these different observation, interventional, and counterfactual distributions. I mean, this is even uncountably infinite if you have like real numbers in your interventions, right? Like you can put it to any number, yeah? This is really like humongous, right? And it's just one SCM, which generates all of this. Remember, statistics, we just had the joint probability, one thing. Here we have like a whole universe of things, essentially, yeah? And the collection of all these things, which we can construct, right? Like we can let a computer run and do this, right? We can construct them through our syntax with L1, L2, L3, as we just defined. If it has the meaning, the semantics, as we have covered in section 2 of this lecture today, then this is what we call Pearl causal hierarchy, right? So essentially all of the different interventions, all of the different worlds, every eventuality, everything which can follow from one SCM, that's what we call the causal hierarchy. So this was just the definition of the so-called PCH, but this doesn't answer still, does it make sense? And so let's conclude this now. So again, is it a hierarchy? Is it a ladder? Is it really such that, you know, L1 is strictly a subset of L2 and L3? I mean, logically, this already seems to be the case now, given our construction. And well, it is actually the case. So in terms of logical expressiveness, a higher rung is always underdetermined given a lower rung. So we'll just do a simple proof for L2, L1. What this really boils down to is finding a counterexample. So finding two SEM which agree on the L1, which disagree on L2, which automatically then means that there can be no implication, right? Because you cannot use this L1 equivalence class to, you know, reason about all of the L2. So M1 is has exogenous terms which, you know, are just again a coin flip, and say X is, you know, the coin flip and Y is just a copy now of X. Looks a little bit artificial now, but it works. So X is just a coin flip and Y is someone just noting down what X was, right? So if, for example, X is 1, Y is also 1. And now we have also the reverse SCM, M2, but here it's a different way, right? Like here, Y is actually the one coin flip and then X is the copy, yeah? In general, what we can see is that, you know, if we do an induction, we're not going to do it here now, but for all the terms in L1, they're going to agree. So both M1 and M2, their interpretations of any of the terms which are possible from our syntax is the same. However, we have the following disagreement. So one model proves essentially that if you do an intervention, right, so X being set to 1, that Y must be 1, while the other doesn't prove that, right? And this is very easy to see. So, and this again also you see in the footmark, the distinction here. Huh? How is this easy to see? Well, if you think graphically now, so X and Y, in M1, X is causing Y, arrow goes to Y, and in M2, it's the other way around from Y to X. And now if I intervene on X, it's asymmetric. I'm not intervening now on Y, I'm intervening on X, right? So I'm setting the value. Well, if I set the value to 1, Y is just a copy of X. So I know Y will be 1. But in the other model, if I intervene on X, I cut the relation to Y. It's not anymore a copy. It's set by me, right? So I don't have the same statement. And this is really what it shows you. There's two different SCMs on the intervention level for the same observational level. And so we see this counterexample. It shows definitely that it's possible. So it's not general. So it's, in a sense, it's strict, but how strict is it, right? Like, can we quantify? How often does it appear? So you remember maybe from last lecture as well, where Christian was also there, and we were talking about, you know, this reassuring result in faithfulness, that it's, you know, measure 0, that, you know, a little perturbation will always get us to have, you know, faithfulness satisfied. And so, you know, we will be able to do causal discovery and talk about these models and, you know, equate graphical statements with independent statements in the distribution. Now we want to have some similar quantification. Ideally, we get a similar result, right? And so what we can do now is quantify this by the notion of collapse, right? So this was all implicit now. Let me just formalize really quickly. So if we have two layers, J and I, then J, the higher layer, J greater than I, so for example, 2 to 1, collapses if this implication holds for all of the SCMs in the set of SCMs, right? Like again, remember, SCM creates all of these infinite distributions, and omega is now, that's why it's omega, it's a very fitting symbol because it's a set of all the SCMs, right? And essentially, if I have any kind of SCM and I consider other SCMs, right? If this implication holds, then what this really tells you is that there is no difference, right? Because, well, I can just go from level 1 to L2. But thankfully, we know collapse is not happening always because we have seen a counterexample. Just to also briefly once more emphasize why collapse is actually bad, right? Like I just told you, it would be fully determining. So essentially, you know, a quantity like this, right? Like a clearly counterfactual quantity, you could suddenly determine just with do operation, right? But this, you know, it would be weird, right? Like if that would be the case, then, you know, we would be screwed in a sense, yeah? And actually, there's cases where collapse can happen. For example, this is a nested counterfactual. Looks horrible, yeah? But you can actually show that this thing is just a regular counterfactual. Yeah? So we want to avoid that a collapse would happen with L2 and L1 and so on. Yeah? We have seen in general that collapse is not always happening, counterexample, but now let's quantify. And with this, I really want to conclude this very dense lecture, but it's also measure zero, yeah? So it's also infinite, just like, for example, for the real numbers, the rationals have measure zeros, but there's, a countably infinite number of rationals, but always doing a wiggle will be fine to get us going, yeah? So this is really what the causal hierarchy theorem is saying, that, with respect to Lebesgue measure of a suitable encoding of, L3 equivalence classes, not important what that means for now, but it just tells you that on the L3 level, that's the highest level, and there we have equivalence classes. If you have a suitable encoding, you can actually show that, these sets are measure zero. Yeah? So really, almost all of the time, we will not have a collapse. And so we can safely say, yeah, causal inference actually makes sense. And just to give a brief graphical or visual intuition, right? So L3, we can usually get, L2, we can usually get from L3 by just doing marginalization, essentially, right? Like we sum up over these different, U terms, which are irrelevant for the moment, and just keep the intervention. That's how you go from L3 to L2. And L2 to L1, you can also do the empty intervention, right? The empty intervention is just like not intervening, essentially. Yeah? And you will always have this picture, essentially. It's a non-injective function going from higher levels to lower levels, right? Like multiple things get mapped into one. And one of the examples we just saw was like this, right? Like we had agreement on L1, for example, but disagreement on L2. Yeah? And that's really what the causal hierarchy theorem proves. Fun fact, the proof, if you want to find it, it's actually not online, and I've not proved it myself yet either. However, this picture here is taken from another paper from a subset of the authors, which did a topological proof, which was shown to be equivalent, essentially. And yeah, so we know causal inference stands, and this is the end. So I just want to give you another comic. Different what ifs and what ifs and what ifs. Nested counterfactuals, but we saw they are just counterfactuals. So yeah, thank you. So Christian, I know it was probably hard to follow because, but they are experts now, like.
I will have lots of questions.
But yeah, so let's take the opportunity. I mean, it's long overdue if you have to leave, but if there's any questions or thoughts, impressions, I know this last part was a little bit dense, but I was just trying to give you the justification. Okay, really, it makes sense, right? Like we have covered the intuition of how they are distinct. We have seen qualitatively it makes sense. We have seen even when we compute it makes sense. But this really proves that it's impossible. You cannot it's actually the hallmark result, because it tells you it's impossible for any machine learning model to just go to interventions or counterfactuals without further assumptions, right? If I have the graph now, if I, or assume at least something, I can work with that. Or if, for example, as we'll see in the very last lecture of this course, large language models, right? Like if they find information about, interventions and counterfactuals, they might be able to exploit it, right? It's hidden in the observational distribution, right? But doesn't mean that it's impossible. Huh? But in general, if we just, technically speaking, it is impossible, right? Like without assumptions. But if the assumptions are hidden somewhere and we can use them somehow, that's a different story. Yeah? But that would mean that there are some assumptions. This result still holds. Yeah? It's consistent. So yeah, causality makes sense. And now you have the framework.